So at the end of the last class, we looked at vectors that took this form. We looked at vectors that took the form chi was equal to L minus 2 plus eta L minus 1, the whole thing square on psi. Right? Okay, this book calls it H, so we'll just call it H. The primary of dimension H. Okay, and when we acted on the state with L1 and L2, and we demanded that annihilate the state. The logic for that was that if L1 and L2 both annihilate the state, then the state becomes a primary. But every primary that was also a descendant, as we discussed last class, is necessarily orthogonal to every vector in the whole module. Okay, so if the state is annihilated by both L1 and L2, then it is a primary that is also a descendant, and hence in particular orthogonal to every vector in the module. Right? The argument that was orthogonal to every vector in the module is very simple. You wrote it as its descendant, and then you took the inner product, flipped the L's because of the dagger, and that annihilated the other states.
These are like pure gate states. Right?
These are like pure gate states, exactly. Louder, louder. They decouple from the theory. It's exactly like states that are BRST exact in the study of gauge theory. This is the reason why we are allowed to change gauge, for instance, because you change, only the BRST. Decouple pure gauge states because they are orthogonal, as you say, the BRST exact states because they are orthogonal to every state of the theory. Okay. Also related to the fact that we are allowed to change gauge because that changes the BRST operator only in a BRST exact manner. Okay. Yes.
So in last class you proved that every state that is descendant and primary is a null state.
Yes, is orthogonal, not only null, orthogonal to every other state.
Orthogonal to every other states in that module.
In that module.
So is the converse also true that if the state is null, your state is primary as well as descendant?
If the state is null, the state will be both a primary and a descendant. Yes, I think it will be true. Now you want to know, you want a proof of that. Yeah, in a unitary theory, the state has to be 0, right? If the state is null. No, but I think it will be true even more generally. Good question. So suppose it is null, then you see, but this, you see, the state is going to be, let's think about that. This state is null, so it's orthogonal to itself. Now, this itself was a descendant. I think it's going to be the case. The way.
So what is our motivation of going in this particular direction then? Why we are looking at the primary as well as descendant?
Because we're looking for null states. That is one way of guaranteeing that the state is null.
Yes.
Okay? If we can, you see, we know that there is a null state here.
Yes.
If
L1 and L2.
No, sorry. What I meant to say is that we know that when the Kac determinant is condition is met, when H is equal to H1 to H is equal to H2 1, we know there's a null state. We want to find this null state. Now there are two ways to go about it. One way would be just look at the inner product matrix and diagonalize it. Okay, the guy with 0 eigenvalue is the null state. That's one way to do it. That would be, we could have done that. Okay. It's not hard. It's just basically, it's not much algebra. It's just that I wanted to illustrate this fact that the way it became null was that it was a primary as well as a descendant. Okay? So we found another way. You see, that way we basically did in the previous class because we found the whole inner product matrix. So diagonalizing it was a simple job, right? Okay? But I wanted to illustrate another point about it. You can ask, what is the mechanism for it becoming null? And the way it worked was that it was a descendant plus a primary. Now, what we did was to find the conditions for this thing being a descendant and a primary. If we find that it's possible to find this, then that state is guaranteed to be null. So we found the null state. Okay? So if we manage to go this way, it will certainly work. I believe the other way is also right, but I won't try to give you a proof now. I'll think about it.
Isn't that like working in Minkowski space? Like you have like an inner product matrix which has like one, let's say one negative eigenvalue. Then you can have a null vector, but that is not orthogonal to all the other vectors.
Well, you have to combine it with the fact that it is part of this representation theorem. Right? This state was null and it was a descendant. Okay? Now, so it's certainly orthogonal to itself. The question is it orthogonal to every other state in the module as well? Okay? I believe it's true. You know, see, the structure of that will go as follows. But let me not try to make a proof on this part. Okay? I could try. I'll try. I believe it's true. It's some algebra which I will try to. But I won't try to produce at this time. Okay? But it was not necessary for this discussion. Right? Because we found a state that was both a descendant and a primary. So that was definitely null. Okay? So for this discussion, that theorem was not required. Is this clear? Okay? So let's proceed with this discussion. But good question. Good question, I'll get back to you about it. Okay. There's probably something simple to say, but I'll get back to you. Okay. So we started with this state. And then we acted with L minus 1 and L minus 2. Sorry, we acted with L1 and L2 on this state. Okay? When we acted with L1, the L1 lowers the energy of all these states by 1. These states had energy h plus 2. So it must give us a state that has energy h plus 1. The only state in the module that has energy h plus 1 is L minus 1 on H. Okay? So when we acted with L1 on chi, we got something into L minus 1 on H. Okay? Similarly, when we acted with L2, that state has a dimension H. Because H plus 2 minus 2. So the only state in the module that has energy H is the primary itself. So we got something. We did the algebra. I'm just reminding you of the structure of the algebra. L2 of chi was equal to something into H. And then what the algebra we did last class was effectively evaluating these somethings. Okay? And we did that. We did that, and we found the following. We found that this was 3 plus 2 plus 4h in the eta, and this was c by 2 plus 4h plus 6h eta. This you might remember I had incorrectly written it as 10, the 4 plus 6, and then somebody reminded me one of them hadn't. Okay, right. So we found this result. Now, question: can the state be null? Can we obey that this state kill the state? You know, can we obey the condition that this guy was 0? We discussed it last class, but I'll just remind you. Our discussion went this way. We had to choose eta is equal to minus 3 divided by 2 plus 4h. Okay? Good. That kills this guy. But what about this guy? Okay? For this guy, we get c by 2 plus 4h plus 6. So now it's minus 6 into 3 divided by 2 plus 4h. Okay? Fine. So this has to be equal to 0. Okay? Now this, when we take this denominator common, we get a quadratic expression on the top. So what we get in order to solve this is a quadratic equation. Okay? And I'm not going to do the algebra here, but it's precisely the same as the quadratic equation we got if you remember when we computed the Koch determinant in this sector, we got a cubic equation. But the cubic equation was h times a quadratic factor. So in the end, we were solving a quadratic equation. It's the same quadratic equation that you get. Had to be, right, if we've done it right. Because this guy, when this condition is obeyed, we certainly have a null vector. And when we have a null vector, the Koch determinant must vanish. Okay? So this is just a check that the two procedures are the same thing, the diagonalizing the matrix and looking at these descendants are the same, they land at the same thing, it's the same structures emerging. Okay? And so from this, we just solving this equation, we get the condition, the relationship between C and H, the relation, the H as a function of C, that we found for zeros of the Koch matrix. Okay, so we get the expressions H21 and H12 from the two solutions of this quadratic equation. Is this clear?
What about h equals 0? There should be h equals 0.
We looked for a level 2 descendant.
Yeah.
Okay? Yeah. So what about h equals 0? Yes. See, the way that h equals 0 is a null state is that the primary itself is null. Okay? So that is not a null state because you're getting a level 2 0.
Because of L acting on it.
Yeah, it's a null state because no matter what you do with your algebra, inner products of descendants are something times inner product of primary. And at h equals 0, the primary itself is null.
Not the primary.
Not the primary.
At h equals 0, the only h equals 0, the first descendant, yes, you're right. H equals 0, we get L minus 1 on, L minus 1. Okay? So what we're going to get there is a structure that is not getting you a level 2 null state.
It was already existing.
It existed and you create that. Okay? Now you could ask, what about at h equals 0, maybe, just a minute, maybe, good question, let me think.
I think this analysis will not give you h equals 0 because we are looking at L1 and L2.
Yeah. But you could ask, what about, shouldn't L minus 1, the whole thing square, have been null? Because L minus, at h equals 0, L minus 1, which is del z, kills the state. Yeah, but, so the way that that's not showing up is that we assumed, you're right. You see, we assumed that we're looking at a linear combination with some non-zero L2 here. This was correct for every possibility except that, you see, we're parameterizing the ratio of these two guys. Okay? This is correct for every ratio except L2 by L1 being 0. Okay? Certainly if we do because we forced there to be an L minus 2 here, we're not seeing this. If we just did this algebra without this, okay, we would get something that would vanish at h equals 0. It would be manifestly vanishing at h equals 0. Is that clear? Yeah, so fine. So by parameterizing it like this parameterization was correct for every ratio of L2 by L minus 1 square except L minus 1 square by L2 being infinity. Okay? So that parameterization removed that possibility, and there was good reason to remove that possibility since we weren't interested in a level 1 null state. We're interested in a level 2 null state. Okay, but excellent question. Okay, thank you. Okay, thank you. Okay, excellent. So let us proceed. Okay. Now, what have we gained from this discussion over and above the discussion we had made 2 or 3 lectures ago, just on the structure of the Cauchy determinant at level 2? What we have gained, the little thing that we could have easily got from the determinant itself by diagonalizing, is the form of the eigenvector that was null. Okay? The form of the eigenvector we now know. This eigenvector is chi, the null state, is equal to L minus 2 minus 3 sorry, what was this here? 3 by 2 plus 4h. Yeah, that's 2, not eta. 2 by 4h times L minus 1, the whole thing square, on h. Okay? This is the null state in our module. This is the particular level 2 null state in our module. Okay? What we're now going to study is the consequences of having this null state. Okay? And the way we're going to study it is to use something we developed in, not last lecture, but the previous one, which was to use what we know is to find the action of L minus 2 on any correlation function involving this thing in terms of differential operators acting on the other operators. Okay, L minus 1 is very simple. L minus 1 was just del z. So we're not going to try to be fancy with that. L minus 1 squared is just del z squared, where z is the location of the operator under consideration, not the other operators. Okay, but for L minus 2, what we do is transfer that operation onto the other operators and use the differential operator that we developed. Okay, so yes.
True that if we try to write down a state at higher levels,
Yes.
and taking all possible linear combinations of those L's into account, will we get only the null states which are coming newly at that level?
No, we will also get the descendant states. Yeah, this is related to the discussion we had. So for instance, L minus 1 squared here would have given you an 8 squared.
But that's the not most generic linear combination, right?
What?
That's not the most generic.
This was not the most general linear combination. But had we allowed for A times L minus 2 squared, L minus 2 plus B times L minus 1 squared, we would have got that as well. So we would have seen 0 null states, you know. But what we would have seen is states that were annihilating the state because some smaller combination annihilated it, and then descendants of that. We would have put the condition that the, I don't know, third, that this was a null state at level 3, but the way it would have worked was that it was a null state of level 2 and a descendant of that. So we would have got that. Okay, but it would have been nothing new. Right? Okay, clear. Great. Excellent. So now what we do is to consider a correlation function of this phi h at z and some other operators, O1, O2. And look at the consequence. Okay, look at the consequence of that statement on this correlation function. So one part of the consequence is very simple. We get minus 3 by 2 plus h L minus 1, del z square. Because L minus 1 was just del z. Okay, the L minus 2 was more complicated, but we discussed exactly how to get that by, doing the contour operation for L, transferring it to the other, all of that. Okay, I'm just going to write down the result we derived. We derived for arbitrary ln's, but specializing to L minus 2, we get sum over I is equal to 1 to n, 1 over z minus zi, del by del zi plus hi over z minus zi, the whole thing squared. You remember these two terms we got, right, from the two terms in the OP of T with operator. Okay, we had more complicated expressions in general, but because L is equal to minus 2, it was relatively simple. Okay, So this full operator on correlation functions has to be equal to 0. Okay, that is the statement that this was the null state. Okay, the null state is null because it just does not show up in correlation functions. Sorry. So I'll just check if it's important. Hello? Hello? Hi, Shayantan. I'm teaching a class now. I'll call you later. If that's okay. Sorry. Okay. Excellent. So this is the equation we have. And equations like this are form the heart of the solvability of minimal models. We're going to start seeing that at work. Okay? So in order to understand what these equations say, let us first look at this equation for phi h basically with itself, but I'll say it more generally. Suppose I take a 2-point function, O1z, z1. Now we know already, because of what we derived 2 classes ago, that 2-point functions can only be non-zero if the dimensions of the 2 operators are the same. Okay, in which case they take the form 1 over z minus z1 to the power 2h. Okay, so let's assume that this, if the correlation function is 0, of course the equation is trivial. Okay, so let's assume that O1 has dimension h, so that this guy is 1 over z minus z1 to the power h. Okay, and so now let's look at this operator. This is a very simple operator because the sum over I is equal to 1 to n is just one term. So it's 1 over z minus z1, the whole thing by del z1, plus h over z minus z1, the whole thing squared, minus 3 by 2 plus h? 2 plus 4h. 2 plus 4h on this object has to be 0. Now, del z square. Thank you. Okay, now let's do the algebra first and then we'll see what we should have expected. Okay, let's do the algebra. First thing you see that each of these expressions is going to result in 1 over z minus z1 to the power h plus 2. Oh, sorry, say again? 2h, thank you. 2h, thank you. 2h plus 2. Right, because every expression has either 2 derivatives and a constant, or 1 derivative and a factor of z minus z1, or no derivatives and a factor of z minus z1 square. So every operation would add up 1 over z minus z1 square to that thing. Okay, so it's just a matter of finding the numbers behind this. That you're going to help me with. It's horrible. So let's see. So z minus z1, del by del z1 gives plus 2h. Okay, it would have given minus, but we're differentiating with respect to z1. Okay, this guy just comes with the factor that you see, so that's plus h. Okay, and this guy gives plus 3 by 2 plus 4h into, now we're differentiating with respect to z here, so we get minus 2h into minus 2h plus 1. Is that okay? And there's a minus here. Okay. All good? Okay. So we take now, there's h, 3h here. We'll just take a factor 3h out. So that's 1 minus, this minus survives, so that's 2h plus 1 over 2h plus 1 into 2, because that's what this this thing is. And there's a factor of 2. Thank you. Because we only took 3h out. Okay, and this is clearly 0. Right, because this thing is 2 by 2. Okay? So in this case, this equation was a little disappointing. It worked as an identity. It didn't tell us anything we didn't know before. Actually, had we tried an operator of dimension h1 not equal to h, it would have been contentful then. But of course, we had simpler ways of knowing that this dimension had to be h. This was a bit disappointing, but if you think about it for a minute, it had better have been disappointing. Because if there was a constraint coming from here, okay, that would have been the statement that these operators, I mean, we would have got suppose we've got a contradiction. That would have been a statement that the 2-point function of this operator had to be 0. Would have meant that this operator could not exist in the theory. Okay? And then we wouldn't have had anything interesting if there were no operators with null states. Okay? Had it been that there were that we'd concluded that there were just no operators with null states, that would have been a bit boring. Right? Because otherwise the operators with null states would have had to have 2-point function. Could have been something intermediate. Could have been that you'd got only for some values of c is it not allowed, whatever. But anyway, this is how it works. Right? We just get this 2-point function thing as an identity. No new information. Looking boring, and you might conclude from this one, extrapolating from this one data point, you might think these null states are not very useful. Okay? This would be a bad misextrapolation. Okay? And in order to see that, let's now look at what happens with 3-point functions. Okay? So, when we look at 3-point functions, we get this. Right? We get 1 by z minus z1 del by del z1 plus h1 now, z minus z1 plus 1 by z minus z2 del by del z2 plus h2 z minus z2 minus 3 over 2 into 2h plus 1 del z squared now on what? Well, we also know the form of 3-point functions. Okay? So this is acting on z minus z1 to the power h plus h1 minus h2 by 2, z minus z2 to the power h plus h2 minus h1 by 2, and z1 minus z2 to the power h1 plus h2 minus h by 2. That clear? There's no factor of half, you're saying? There's no by 2, maybe that's right. Let's add up. We should get that the sum of these three is h1 plus h2. You're right, no by 2. Thank you. Thank you. The sum of these three should be the scaling dimension h1 plus h2 plus h3, and that works if you don't. Yeah, correct. Thank you. So we know that it has to act on this. Now, question, when we do this differential operation and we act on this, do we get something trivial or not? Okay. First thing here is that different terms give different structures. See, for instance, multiplying with this guy gives an extra factor of z1, z by the z1. What? This is square. Thank you. Thank you. Yes, square. Thank you. Would give an extra factor of z minus z1 square. Taking derivative would give more complicated factors, right? Okay? So when you act with this operator, you get different algebraic structures. Of course, it's a simple matter to do this or put it in Mathematica. Okay, you'll get what you get. I'm not going to try it here. There's no point. I'll just tell you the result. Okay? The result is that all of the different structures you get, vanish if and only if one condition is obeyed. Okay? You know, you get various structures with coefficients, all of which vanish okay, all of which vanish if and only if we get the following: 2h plus 1 into h plus 2h2 minus h1 equals 3 into h minus h1 plus h2 into h minus h1 plus h2 plus 1. Okay, is everyone comfortable? Would you like me to check this for one structure, or can we just move on?
Is this the only condition?
Only condition. Many different structures, all of which have the same coefficient behind them. I mean, all of them have proportional coefficients. So the coefficient for all of them vanishes if this one condition is obeyed. Okay, not clear until you do the algebra. Is this okay? Would somebody like me to check out? Will take 15 minutes. There's no point. Let's move on. Okay. What?
Is this like at any level A, are we getting like L minus 2 sort of constraints like that? Because we know for the 2.0
Something like that. I will tell you about the kind of constraints. Oh, you mean for 3 points? For generic endpoints. For once you go to 4 points, it will be more interesting. You see, 2 and 3 were special because the form of the function was determined by conformal invariance. From 4 point on, we've got an unknown function of cross ratios. Okay? So from 4 point on, when you act on this condition, it will not give you constraints on h's. What it will give you is a differential equation that determines this unknown function of cross ratios. Okay? So 2 and 3 were special from that point of view because even though we had a differential equation, we converted it into an algebraic equation because we knew from other considerations what the structure had to be. Okay? From 4 point onwards, the differential equation will remain a differential equation. And indeed, the solution of the differential equation at the 4 point level is key to the solvability of these things. It will give you what you might loosely call minimal conformal blocks. And we'll study this in great detail as we go.
And what about these constraints at higher levels? If you want to concentrate only on 2 and 3?
Yeah. So now, if you have higher levels, you will get additional constraints. I will tell you about the form of these constraints at level r comma s for the 3 point functions. For 2 point functions, you never get anything. Okay? 3 point functions, you get a slightly different constraint. So we work this guy out, and then I will tell you about the structure at higher levels. Yes?
So 2 point function was more constrained, even more than the 3 point function. That's why we were able to fix the weights. That's why we got a trivial condition in the identity in the definition where you are getting a condition.
Yeah, in some sense, the only condition we could have got, had we been doing it for the 2 point function, is a condition on h itself.
That we already got.
Yeah, but it could have been, you see, we got h as a function of c. But could have been that you got some condition that tells you only particular values of c are okay. Okay, yeah, but it's not how it's happening. It's true that there was no h1 left over there. Here there's an h1 and h2, and that is what gives you, not constraints are not over tight. Clear? Okay. So if you just do the algebra, this is what you get. Now, this condition looks very complicated.
Why is this not symmetric in H2 and H?
Presumably it is. Yeah, presumably it is symmetric. See, neither side is symmetric. It has to be symmetric. Just written in a way that you get it when you do some algebra. I think if you work it out, it will be symmetric. Okay, in fact, maybe there's a form here that's symmetric. Let me show you. Yes, ma'am. No, there's no form here that's given that. The way it is given, anyway, has to be symmetric. You do it the non-symmetrical terms of it. Yeah. It will be, it's just not manifest. Okay, excellent. Now, what is the logical structure of this equation? Okay. The logical structure of this equation is that it gives you one constraint on the 3 dimensions involved. So we'll regard this as follows. We'll think of this as determining H2 given H and H1. Okay, so if I look, so what is this telling me? The first thing that it's telling me is that you cannot have a 3-point function of our special operator with 2 arbitrary operators. Unless the dimensions of those 2 other operators obey this equation, you cannot have such a 3-point function. And I want to know a little bit more precisely what this is telling us. So the way I formulate it is I try to determine H2 given H1 and H. Now clearly this is a quadratic equation in H2. H2 squared, and then there's an H2 here. So you'll get 2 roots. Okay? You can solve for this, and I could write down the solution, but it's not very illuminating. I'm going to tell you about the solution in language that will be more illuminating. Okay? And for that, I'm going to have to remind you of formulas I've written down maybe 3 times already. But I'll remind you of these formulas. I'm reminding you of the zeros of the Koch determinant. HRS of C was equal to H0 plus 1 by 4 R alpha prime plus S alpha minus the whole thing square, where H0 was equal to C minus 1 by 24, and alpha plus minus was equal to square root of 1 minus C plus minus square root of 25 minus C divided by square root of 24. We will also need the other forms by and by, but at the moment let's stick with this. Okay? Now, our H was either H21 or H12. Right? Because our H was a solution of this Koch determinant at level 2. We got that from either H21 or H12. So our H is equal to, and 2, 1, 1, 2 are basically these. Anyway, let's write it down. H is equal to C minus 1 by 24 plus 1 by 4, let's say 2, 1. So square root of 1 minus, okay, 2 alpha plus alpha minus the whole thing square, where this was this, or one off. Okay, 1 of this, or C minus 1 by 24 plus 1 by 4 alpha plus 2 alpha minus the whole thing square. This was our H. Right, this is the operator that we, this phi H. Now, what we're going to do is to parameterize H1 and H2 in a sort of similar manner. Okay? So what we will do is to say let's define H alpha to be equal to H0. This is the same H0. Okay, this is H0. That thing there. Okay? H0 plus alpha squared divided by 4. Okay? This is just a relabeling of H. You give me alpha, I give you, I give you alpha, you get your H. Okay? Now, we do this for H1 with parameter alpha 1 and H2 with parameter alpha 2. Okay? Plug that into this equation here and solve for alpha 2. Okay? Solve for alpha 2 in terms of alpha 1 and the data that gives you H. H is something fixed, right? So solve for alpha 2 in terms of alpha 1. Okay? This is something you can do. When you do that, you find the following.
Plug H in H2 in this equation.
What?
Plug H alpha in H2.
And H1. So H1 is equal to H0 plus alpha 1 squared by 4. H2 is equal to H0 plus alpha 2 squared by 4. Plug them both in and solve for alpha 2 in terms of alpha 1 and whatever else appears. Clear? Okay? You find the following two solutions. So you get different solutions depending on whether whether we are using H with H21 or H with H12. So suppose H is equal to H21. Okay? Then we get alpha 2 is equal to alpha 1 plus minus alpha plus. And if we use H is equal to H12, we get alpha 2 is equal to alpha 1 plus minus alpha minus. H had to be either H21 or H12 because it had the null state. These are the two options. See, so in these alphas, the condition on these 3-point functions becomes a very simple one. Is this clear? I'm sorry I'm not doing all the algebra here. It's just that the algebra would be pointless to do. What matters is the logic. Okay, I don't like this, but I feel we will just take many extra classes if we do the algebra. I'll get it wrong, you'll correct me, okay. Fine.
Alpha 1 takes what value? Any real value?
Any value. Yeah, any real value. This was just, solving in terms of, you give me alpha 1, I'll give you alpha 2. Okay? Excellent. So, we write this equation in the following form. Phi 1 2, maybe we write 2 1. 2 1 phi alpha is equal to phi of, here we got alpha plus alpha plus phi of alpha minus alpha plus. And phi 1 2 times phi alpha is equal to phi of alpha plus alpha minus plus phi of alpha minus alpha minus. What do I mean by these equations? What I mean by these equations is that when I fuse phi 2 in the sense of the OP, I take the OP between the operator phi 2 1, the guy that has H is equal to H2 1, and some arbitrary phi, which has dimension h alpha. That was what we called alpha 1 originally. Right? Then the only primaries I will get in this process that I might get, some of these may have may appear with coefficient 0, but the only primaries that I could get are a primary with h given by alpha plus and h given by alpha minus alpha plus, and similarly for h12. Is this clear? Because the fusion is proportional to the 3-point function. If there's 0 3-point function, you will not produce that OP will not happen.
Which operators are you fusing to?
I'm fusing h with alpha, which we call alpha 1 initially. Okay, but it works for any alpha. That's why I've written as alpha, not alpha 1.
By fusion means you are taking OP of 1 H alpha, 1 H with 1 H alpha.
Exactly.
So you are like taking 2-point function.
I'm taking the OP. Remember our discussion of the OP? We put one operator here, we put another operator here, we do the path integral in disk. That gives you another effective operator at the origin. So the effective operators have to be either this guy, this. Now, of course, you see, when we get this statement, what we really mean is the effective operator has to be either this primary or any of its descendants. I'm talking about conformal families here. Okay? But only 2 conformal families can run in the OP of phi with phi 1, with h with h alpha 1. This is an extremely powerful statement already. If we take phi alpha to be identity, yes. Yeah, let's check what value of alpha is identity. So identity, was it right that 1, 1 gave us identity? That is my, I take phi alpha to be, okay, good, let's try that exercise. I want to know what value of alpha will give you h equals 0, right? So we have h naught plus alpha squared by 4 is equal to 0. Okay, h naught was c minus 1. Note that h naught is negative. Okay, c minus 1 divided by 24. 4. So let's call 1 minus c divided by 4 has to be alpha squared by 4. And in that case, we get alpha is equal to square root of 1 minus c divided by 6. That's same as r equals 1, s equals 1. Right. Now, let's look at what happens for this value. That is r equals 1, s equals 1, because, let's look. Because when we take 1 and 1, we'll cancel the square root of 25 minus c. We will get, let me just check that. We get 2 square root 1 minus c divided by square root of 24 into 1 by 4, so half. So that, and then this is square root of 6, so 1/4. And then from h naught we got no, but we just should be comparing with the alphas. Sorry, we got square of this, right? Excellent. We got square of this. I messed up some 2's and so on. Okay, but I think it's right. It's 1 comma 1. Okay, so now let's do that. If it's 1 comma 1, then our effective value of alpha there is alpha plus plus alpha minus. Right? So, in that case, this thing becomes what? This becomes we get phi of alpha plus plus alpha minus plus alpha plus, or plus phi of alpha minus. Okay, right? Because minus alpha minus. No, this was alpha plus plus. Yeah, phi of alpha minus. Now you are asking if I did. My original operator was, what was it? 2 alpha plus plus alpha minus, right? So we got 2 alpha plus plus. So this guy is the original operator. This is phi of 2 alpha plus plus alpha minus plus phi of alpha minus. Right? So this is what we expect. This is not what we expect. But you see, this algebra has only told us what is possible. These are the structures that will be allowed by this differential equation. It's not told us that every structure that's allowed will actually occur. The coefficient of this structure might be 0. Nobody can stop that. Okay? So in the case of identity, this is the one we want, that will be there. The other coefficient will be 0. In fact, in 5 minutes we will find some of the ways of thinking of how you get these zeros. Sorry, you had follow-up?
I was thinking that if phi alpha is identity,
yes,
then the constraints that we put using this L0, L-1 and L1,
yes,
they answers to tell you that the other operator has to have some particular.
exactly. You know, the way it's going to work is that when you have identity, you've got a second null state, which is L minus 1 on identity is 0. So there's a second constraint on this OP. We've looked at the constraint because this H has a null state. But in the case that it's identity, the other guy also has a null state. Okay? So if you put those two together, you will find it's only this. Okay? We'll see more of this as we go on. That's more or less what you said. Yeah. Okay. Other questions or comments?
So when we do 3-point function in CFT, we also get the structure constant.
Yes.
Are we about to
This analysis that we are doing cannot constrain structure constants because it's homogeneous in the structure constant. What will constrain structure constants is the analysis of the 4-point function. Of the 4-point function. You see, when you look at a 4-point function, that 4-point function is expanded in blocks timesCijk square. Okay? And the fact that this, with someCijk square with the exchange of one guy plus someCijk square with the exchange of another guy and so on, has to obey a differential equation, tells you about the relativeCijk squares. So theCijk squares will get constrained, but from the study of 4-point functions, not from 3-point functions. Okay? Excellent. We will see that as we go along. So when we analyze we looked at this differential equation and applied it to 3-point functions. There's a similar analysis we will do at some point, but we will apply it to a 4-point function, and we will see how that constrains the structure constants.
Is this some sort of analogous to the Clebes-Gordon sort of?
Yeah, very good. So it's true. There is an analogy which is close in some respects and less close in other respects. So let me take a few minutes to talk about that. Suppose we had SU2 and we wanted to ask, what do we get when we fuse J1, J2, J3, J4? What are the singlets? Fuse just means they're singlets. Can we write down a basis of singlets in the tensor product of J1, J2, J3, J4? There are, all of you know the singlets of 3 j's, right? j1, j2, j3. Okay, using that, you could proceed as follows. Using that, you could proceed as follows. You could go like this. Say we want to look at the singlets in j1, j2, but j1 tensor j2 is equal to sum over j1 minus j2 mod to j1 plus j2 j. Where j is equal to, Okay, this we know. Then we could say j3 tensor j4 was equal to sum over j is equal to mod j3 minus j4 to mod j3 plus j4. J prime, let's say. So we fused these two, we've made representations of these things. Now we want to find a singlet in the product of j with j prime, where j and j prime run over these values. But in the product of two j's, there's a singlet only when j is equal to j prime. That follows from the same rule. Singlet means j1 minus j2 is equal to 0, but that only occurs if j1 is equal to j2. Okay, and therefore those values of j that occur both here and here each give us a singlet. So for each value of j that it lies both between mod j1 minus j2 and so for j greater than equal to max of j1 minus j2 and j3 minus j4 and less than equal to min of j1 plus j2 and j3 plus j4. For each one of these j's we get an independent singlet. Is this clear? Now some of you are thinking, well, that's okay, but you've made an arbitrary choice here. Because we had 4 representations, all of which were on equal footing. You chose to group them as j1 with j2 and j3 with j4. What if I group them with j1 with j3 and j2 with j4? I will get a similar, you could do the similar, you could get the fusion. And you get what looks like a different answer. The number, however, of what lies between these, you can check for yourself, is always the same. Because the total number of singlets is an invariant thing. Every correct procedure of determining that number should give you the same answer. And you do get the same answer. Moreover, you are often interested not just in the number of singlets, but in the form of the singlets. How do you contract indices to make the singlets? Each one of these procedures has a particular singlet. Because you see, when you fuse j1 with j2 to get j, it comes with a Clebsch-Gordan coefficient. You fuse j3 with j4 to get the same j, it comes with another Clebsch-Gordan coefficient. And then to get the singlet, you just contract m with minus m. So these formulas here come with an instruction for how to produce the singlets. Is this clear? If you knew the 3-point, the Clebsch-Gordan coefficients, which all of you have studied in quantum mechanics, you could use those Clebsch-Gordan coefficients to make the singlets. Roughly speaking, it's C, J1, J, J2, J, C, J3, J4, J, and then with the indices contracted. Okay, in the appropriate way. You know what I mean, right? Excellent. Now that gives you one basis in the space of singlets. You get another basis by first fusing J1 with J3 and J2 with J4. Okay, and the fact that these are both bases in the same space, namely the space of singlets in the tensor product of these 4 J's, tell you that there is some change of basis going from one basis to another. And this change of basis is what's called a 6J symbol in the study of SU2. It's called 6J because it needs the elements of this change of basis need specification of 6 J's. You see, because you can take J1 with J2 and fuse via J, or J1 with J3 and fuse via J prime. Okay, and the change of basis will tell you how the first guy is written in terms of the second guy. So it will be a matrix whose dimensionality is the number of singlets, matrix in this J prime space, but labeled by J1, J2 on one side and J1, let's say J3 on the other. So you see the net thing is specifying 6 J's because the 4 external labels and the 2 matrix labels, all of which are J's. It's called a 6J symbol. It's a very beautiful object if you're not familiar with this, even in the study of classical group theory. Okay. Now, there are many parallels between this structure and what we do in conformal field theory. And those parallels were foreshadowed in the words I used for telling you about SU2. I said you fuse J1 with J2. That's the language we use in OP. Okay? So, making 4-point functions out of fusion of operators is very similar to making singlets in SU2 out of fusion of J1, J2 and J2. And the fact that you can get the same answer this way or that way is similar to crossing symmetry in the conformal field theory. Okay, so there are many similarities. In fact, there is also selection rules. You see, I'm regarding this J, in some sense, you could say selection rules for what quantum number? It would be for the quantum number J1 plus J2 the whole thing square. Because J1 plus J2 the whole thing square is J into J plus 1, where J runs over these values. J runs over these values. So in some sense, these are not, in some sense, there's something you know about the operator. Actually, in fact, this quantity has a very clear analog in study of conformal blocks. It becomes the Casimir of the conformal group, and is one way that people becomes a differential equation that people use to solve to determine conformal blocks. So the fact that this is J1 plus J2 square has a conformal analog. In some sense, the answer is yes. Is this clear? Okay. So there are many parallels of this structure, and in fact, there's one more parallel, which I don't want to oversell, but one more parallel is that finite dimensional representation theory is full of null states. The fact that your representations are finite dimensional is a consequence of having null states. Okay, so that is in some sense paralleled in these minimal models. Okay, and one last thing, the conformal bootstrap problem can be worded in the following. Maybe I'm saying too much now, but let me just say it anyway. The conformal bootstrap problem can be worded in the following language. Once you determine the 6J symbols, what are the 6J symbols for conformal field theory? The 6J symbols for conformal field theory would be, can you write the conformal block of fusing 1, 2 with 3, 4 as a linear combination of conformal blocks of fusing 1, 3 with 2, 4? Now, conformal blocks are much more complicated. I'm saying this, we haven't even defined conformal blocks, okay? Just saying this for the people who know what it means, just since you asked the question. Okay, we'll come to all this. But the conformal blocks are much more complicated objects than Cij,k. In particular, they depend on position. And the question of what you mean by the statement is a tricky one, because not every family of functions forms a basis for all functions and function space and so on. But there is a sense in which you can define these 6J symbols in conformal field theory. In fact, the world expert on this is Abhijit, our faculty member. Okay, and you can reword the whole conformal bootstrap problem with making some assumptions entirely as an algebraic problem onCijks coming from these 6J symbols. This rewording has more or less been done in a paper Abhijit wrote. Making that useful has never been done.
The paper is called In Search of CA.
Yes. Okay. It's a beautiful point that he makes there. So, there may be a way of wording and solving the conformal bootstrap problem, which is similar to Lie or whoever did it, Katan, I don't know, the people who classified Lie algebras. I won't take names here. Because what they did was to, anyway, I'll stop talking. I'll stop talking. We'll come back to such matters as we go along. This is, I feel, a very interesting question, one with great structure that someone with a mathematical mind might just be able to solve. I'll say one last thing. The last thing is that, look, there are some kind of problems that physicists are good at, and other kind of problems that mathematicians are good at, in my opinion. Okay? The kind of problem a physicist, or at least my kind of physicist, is good at is, something's here, what happens when it moves there, infinitesimal variations, motion in time. That's, physicists are trained to think like that. If you're a physicist like me, you like thinking about such problems. The kind of things that mathematicians are good at is doing magic. You've got a set of equations, find all solutions of these equations. They're nonlinear equations. How the hell do you find all solutions to these equations? But sometimes mathematicians manage. And an example of this was the classification of Lie algebras. Classification of Lie algebras can be thought of as finding all solutions to the Jacobi identity for structure constants. It's nonlinear equations because of Jacobi identity. Okay, I mean, you gave it to a physicist like myself, you would stare at the nonlinear equation, maybe do some perturbation theory, and then give up. Mathematicians sometimes are good at doing this kind of thing. Okay? What I wanted to say from this big preamble is that it may be possible, and it's half done in Abhijit's paper, to reword the problem of finding all fixed points of the renormalization group in this language. In a language that is very similar to writing down Jacobi identities for the structure constants of Lie algebra. Solving, in some sense, all solutions of these equations are putative conformal field theories. I say putative because there may be further constraints on conformal field theories than crossing. Certainly in 2 dimensions there is also modular. But at least all solutions of crossing. So, just transforming these equations into concrete equations that you can present to a mathematician. With no twiddle signs, I think would be progress. I don't think that's exactly been accomplished. Maybe what I'm saying, the language I'm suggesting is not exactly the right language, but something like this. I feel that one day we will have a solution because of some mathematical magic. Maybe. Okay, this is the kind of problem you can imagine that a mathematician will solve. Maybe one of you is the kind of person who can solve something like this. I know I can't. This is too magical for me. Okay. So sorry, away from this slight of fancy, let's get back to these minimal models. Sorry. Okay, were there any other questions? Sorry about this. Okay. So, where are we? Yeah, so we were at this fusion rule. Okay, so now, okay, we've got this nice fusion. Okay. Now, one of you already asked the following question. Okay, one of you already asked the following question. Suppose we weren't at level 2,1 or 1,2. You had some higher level null state. Let's say it was at level r, s. Okay, what is the generalization of the structure? Okay, so at the moment I'm not going to try to derive it, I'm just going to tell you what the answer is. Already saying the answer is a bit complicated, so let me just tell you. So what we want is phi r, s with phi alpha. Okay, I'm going to write down the answer and then we'll look at it for a minute. First, what we have here is phi of alpha plus k alpha plus L alpha minus. Okay, now what is k? k is summed from 1 minus r to r minus 1, but k plus r is odd. Okay, and similarly L is summed from 1 minus s to 1 plus s, but L plus s is odd. Okay, so we go in this range, but sum only over odd values of, so let's write. Okay, so for instance, here the lower limit L plus s is 1 minus s plus s, and so that's odd. Okay, the upper limit L plus s is 1 plus 2s, and so that's odd. So we start with 1 minus s, and the next value will be 1 minus s plus 2. Next value will be 1 minus s plus 4, and so on, up to the point we get to this. Okay, claim this is the fusion algebra in general. In order just to get a sense of it, let's work it out for phi 2 1. This is for every r and s. Let's work it out for phi 2 1. Okay, so phi 2 comma 1, phi alpha, according to this, now what? So r is 2, so k starts at 1 minus 2, so minus 1, and it ends at r minus 1, so 1. Okay, k is equal to minus 1 to 1. So basically there are two values for k. K is minus 1 or 1. So k is equal to, yeah. What about s? Okay, L starts from 0 and ends at 0, because s here was 1, sorry, 1, s minus 1, yes, thank you, that's it, yeah, 1 minus s to s minus 1, yes, thank you. Okay, it starts at 0 and ends at 0, so L is always 0. Okay, so the two values of k and one value of L. The two values of k are minus 1 and 1. The value of L is 0. And so we get phi of alpha plus phi of alpha minus alpha. Exactly as we had above. Similarly, if you work out phi 1, 2, you get phi alpha plus alpha minus plus phi alpha minus alpha minus. So this is that kind of generalization, right? You get alpha plus some number of alpha pluses plus some number of alpha minuses. Exactly what you get is according to this rule in the books. Okay, how we get this, we will see as we go on. Okay, the study of these minimal models, as you see, is a very complicated subject. It's complicated and a subject about which lot is known. So if we started doing detailed derivations at the beginning, what will happen is you will miss the structure of what's going on. So the plan is to follow the yellow book, which does the first, it's chapter 7 of the yellow book, gives an overview of what's happened. And then chapter 8 goes into deriving more the detail, the specific results in more detail. Okay, that's the structure I'm following. Okay, so some of these things that we say can be shown, we will show, but not just now. Is this clear? Okay, great. Fine. So we have the structure. So what? Okay? The first thing that this tells you is that every time you've got some object with a null state, this some object with a null state, okay? One of these guys with a null state, these phi's, is 3-point function with other operators always have this constraint. Okay? Now, one thing we want to notice is the following. Suppose you look at the operators of the form alpha is equal to R alpha plus S alpha minus, where R and S are integers. Remember that in our study of unitarity, this was the kind of operators we found. Okay, so using that as motivation, let's look at these things. At the moment, we're not putting all the detailed restrictions of unitarity. We're not putting the, bound on that R and S are positive and that they're bounded in some way. You remember what those were. I'm not putting that, but motivated by the study of unitarity, let's look at this structure of operators where R and S are integers. One thing you notice immediately from this, from that formula in the box, is that this set of operators is closed under OP. Because what we do there is add some integer number of alpha pluses and some integer number of alpha minus. So if your alpha start out as being integer times alpha plus another integer times alpha minus, OPE keeps that closed. So you see, already we found something really interesting. We found that there is a closed, perhaps subset, in the operator product expansion, closed to operators that have the structure with integer values of R and S. Okay? Okay. Now, these discussions will lead us into the study of, Notice Notice, of course, that when we look at operators with R and S being integers, these are precisely the weights of that appear as zeros of the Cauchy determinant. Right, so the Cauchy determinant has zeros at R and S equals integers. Okay, because of that, when you do this OP, what you're finding is that if we let's look at this subsector for a moment. Let's look at alpha also being of the form some R prime plus S prime. Okay, now this OP here in that subsector has a second constraint. The second constraint is that the constraints that we should be able to look at the OP the other way. Use the alpha with its R prime and S prime as the first operator, and alpha phi with its R and S as the second operator. We get something else on the right hand side. Both expansions must be correct. Okay, both expansions must be correct. Now, this could work in two ways. It could turn out to be automatic, or it could give you a constraint. Turns out it gives you a constraint. Okay, yeah.
Also, this equality as such should be thought of as containment, not equality.
Not equality, exactly. As we saw in the case of the identity. Okay, case R is equal to 1, S is equal to 1. This is all possibilities that can occur. Whether they will occur, this kind of analysis cannot rule out. Right, because all we are saying is that the 3-point functions are some coefficient times this structure. that nothing can stop that coefficient from being 0. Okay, so now
That way, the OP of phi RS with phi R prime S prime is a linear combination of some these R and S is a statement that the OP of null states with null operator is a linear combination of null operator and stuff.
yes, exactly. The statement is exactly as you said, that you have an operator which has a null state at some level, and an operator which has a null state at some other level. Every operator you get on the RHS is an operator which has null state at some level. Okay? It's remarkable, right? Already the statement is remarkable. Okay, now we're hitting our unitarity bound, and I wanted to talk about the unitary models, which is a long. Okay, so I wanted to develop on this subject and to talk about unitary models. Minimal models. Then, in general, non-unitary minimal models, and then discuss which of these become unitary. We'll do that next class. Yeah. Okay. Any questions or comments?
The expression of this fusion, so these are the most singular terms that are.
These are the only terms.
These are the
Only terms. These are the only dimensions at which 3-point functions exist. Okay, it's not about most singular. It's the only one. Right? Because we are asking, when you have a 3-point function, can its coefficient be non-zero? It can only be non-zero when this happens. Okay? So this already tells you that something interesting is going on, because it tells you that the number of families that appear in fusion of these operators is necessarily finite. In general, if you fuse one operator with another in the conformal algebra, unlike SU2, you get an infinite number of conformal families. This finiteness is, part of the solvability of these theories. Is this clear? Okay, we will come back to this question, to the study, in particular the study of these in general non-unitary minimal models, and then the unitary versions of those, and their Landau-Ginzburg descriptions next class. Okay, any more questions?
Why C greater than 1 theories need more symmetries in order to solve?
Because they don't have null states. Right? We saw that Koch determinant has null states. I mean, the Koch matrix, the inner product matrix has null states for C less than 1. And we are already beginning to see the power of these null states. Right? These null states give you an equation, a differential equation for correlation functions. And you see how powerful these differential equations are already. We've only scratched the surface of the power of these equations. But already you see that there's something interesting happening. We're going to use these null states to solve the theory in a crucial way. Okay, the lack of null states makes those other theories as difficult as any other field theory.
So the number of these constraints that you get at some particular C, let's say C equals half.
Yes.
So the number of constraints that you get is are 2 or 3, I guess. Last class we discussed.
Well, the total
number of these H weights.
Yeah.
1 to 1.
There will be 1 by 16, 1 by 16 basically.
Yeah.
And half. Yeah, 1 by 16 and half. 1 by 16 and half, or 1 by 8 and half. Yeah.
So those will give us limited amount,
limited amount of equations, but there are also limited number of observables. Because the only observables in this theory are the correlators of these 3 operators. Right? So each observable has to obey multiple differential equations. That's enough to determine the solutions.
And that's why we can't do for C greater than 1, because we have
For C greater than 1, you're on your own. Roughly speaking, these null states are equations of motion. They're telling you that an operator, some derivatives on an operator, something on an operator annihilates it. What we're discovering with minimal models is operators which have non-trivial equations of motion, non-trivial sort of Schwinger, quote-unquote Schwinger-Dyson equations, which is so constraining that we can completely solve the theory. In general dimensions, you see, let me say that again. You see, in a normal quantum field theory, normal conformal field theory, the basic field that is used to make the operators, let's say phi in Wilson-Fisher theory, obeys an equation of motion. Del square phi is equal to phi cube, fine. Okay, there's a quantum version of that equation of motion, but something like that. However, the operator phi square obeys no such equation of motion. Okay, no such simple equation of motion. Okay, it's not like del squared on phi squared converts that into some other simple operator. So general operators in the theory have no null states. That's another way of saying it. Whereas these operators are near to having a null state, maybe some deformed way. Okay, in minimal models, every operator in the game has its equation of motion, has its null state. Okay, that's extremely powerful. That allows you to solve. And moreover, we know the form of the equation of motion. I said this about Wilson-Fisher theory in some in principle way. We don't really know the form of the equation of motion for Wilson-Fisher theory because classically it's del square phi is equal to phi cube, but that gets quantum corrections. We don't know we can't control those quantum corrections. Here we know the form of the equations of motion just from unitarity. These equations basically allow you to solve the theory. Okay, that is just not C greater than 1 from that point of view is as difficult as any other conformal field theory. Okay. It's a bit easier because holomorphicity. But holomorphicity, so what? There are still functions you need to solve for. You're on your own. Okay? Any more questions, comments? Okay, excellent.